so you have this phi and this vector A. Okay, so these are not observables. You don't measure actually phi, and you don't measure actually A. What you measure, if you need to measure, you measure the difference between the potentials. So you always measure the potential difference between 2 points. Okay, so that is a measurable quantity. When you measure the potential difference, that actually gives you the electric field. Yeah? So how is okay? If you remember, so let's say in the static case, so the electric field is usually it is this object. So that means the gradient of phi. Clear? So if you are having 2 points, let's say, so you calculate the potential at this very point, calculate the potential at this point. What is measurable is the difference between these two, potential between the 2 points. Potential difference, but you measure actually by, let's say, voltmeter you take, and in a given circuit you measure actually potential difference. Is that true? Clear? But as such, this phi is not a measurable quantity. It is not a physical observable, and similarly A is also not a physical observable. Clear? Okay, so that means if they are not physical observables, there is an arbitrariness. Okay, you can change these phi's and A's in an arbitrary manner such that they can give you different values of phi and different values of A can give you the same field. Clear? Okay, now let's take this thing. So how we define electric field? It's something gradient of phi minus 1 by C partial A by partial B. Clear? Now let's say if I change, forget about A, if I change phi by a constant amount. Let's say if I change phi to some phi plus A. Is that true? A is a number. Okay? It is just a constant quantity. Such that the differentiation of this A is 0. Okay? Not the gradient of this A is 0. So it means phi and phi plus A will give you the same field. Is it right? Clear? So what I am saying, okay, let's look at this formula instead of that. Let's change phi, okay? So this phi gives you the electric field E, okay? So if I now change phi to, let's say, phi plus A, okay, or something, let's say some another function, okay, by some constant amount for the time being, let's say, by constant amount I am changing phi. So what will be the field due to this phi plus A? It will be same thing, is it? Because gradient of A is 0, so you will be having the same field due to this phi plus A. So that means I can change this phi arbitrarily. Okay, so or in other words, the different values of phi gives you the same electric field. Okay, got it? Okay, similarly I can change A arbitrarily. So there is an arbitrariness in A. Okay, let's say for A, since let's say to this A I can add some function which is only the function of x. Okay, not on time, such that the partial derivative of phi is equal to 0. Okay, so that means this A and this A plus phi gives you the same field. Clear? So much over? So it means I am having some arbitrariness. Okay, so how to remove this kind of arbitrariness? So this kind of arbitrariness is fixed by a concept of gauge. So this arbitrariness actually, it means if you change phi or if you change A, it means I am actually changing the coordinates, is it? So it takes a coordinate dependence. But if you look at the action, when I, okay, let's do it first, then I can come to this point. Okay. Okay, so our B is defined this way, curl of A. Now if I can take this phi and A in this fashion, I can fix phi and A. Okay, let's change phi to some phi prime. Okay, this is phi minus 1 by C, some partial, let's say some theta, okay, by partial P. Okay, so theta is some function, some arbitrary function. Let's write, instead of theta, let's write F. Or you can write chi. Okay, F is some arbitrary function. Okay, I am changing this phi by this much. Okay, and A I am changing A plus gradient of this. Okay, so this is a simple transformation. So this fixes my what? Phi. Okay, now if I change phi and A in this way, my E and so this gives me the same field as phi and A. Okay. Okay, now let's check. So therefore I can write this E will go as E prime. Okay, so what is that equal to? What is E prime? So it's minus nabla phi prime minus 1 by C partial A prime by partial T. Okay, because I am changing only the field. I am not changing the coordinates. I am changing only the value of the fields. Clear? At a given point. Okay, so it's minus gradient. What is phi prime? Okay, it's phi minus 1 by C partial F by partial T minus 1 by C partial by partial T. A prime is what? A plus. A plus gradient. Okay, so what it yield is gradient of phi plus 1 by C gradient of partial F by partial T minus 1 by C partial A by partial T. Okay, minus 1 by C partial by partial T gradient of F. So this term cancels with this term. So what I am having? Minus. So it means it gives rise you to the same electric field. Okay. So that is same as E. So that means if I can define my phi and A up to this very arbitrariness, okay, if I fix my phi and A in such a way, it will give me the same fields. Okay? So these kind of transformations we call gauge transformations. Okay, I'm gauging the fields. Clear? In older literature you can see this is known as gauge transformation of second kind. Okay, so in Griffiths you will see actually we will simply call it as a gauge transformation. Okay, what is its physical? I will tell in a moment what exactly it means. Okay. Similarly, now let's take this B. Okay, so B prime will be simply what I am changing. Only I am changing fields at a given space time point. Okay, I am not changing the coordinates. So it means it is some kind of intrinsic symmetry at that very point, or the intrinsic symmetry for the field defined at a given point. Okay, so we'll do it. I mean, when we'll take the Noether theorem, there it will be very much clear what exactly these things mean. Okay, so it is, what is this thing? A plus gradient of F. Okay, curl of gradient is 0, so it is same as like this thing, so that. Okay, clear? So much, okay. So if you can, okay, now let's look at the action. So this action, okay, we have only done action till how, okay, we have done action for free particle, action for the charged particle coupled with the electromagnetic field, is it? The interaction part. We have not done the action for the field itself, okay? So that we are going to do today, but let's take the action, okay? So you are having this action as LBT. Let me do it in a gentle way, okay? Let's do this. Okay, so you can, from this action, you can derive the equations of motion, okay? Yes. If you know the equations of motion, okay? Let's say if you know the equations of motion, from the equations of motion, you can construct actually Lagrangian. Okay, let me give an example. Let's say you know the Newton's laws. So so minus V of x, V dash of x. Is that so? So this is the Newton's law. Okay, so these are the equations of motion you know at hand. Okay, so what would be the Lagrangian corresponding to this thing? You can guess it. Okay, so you can say the Lagrangian corresponding to this thing will be simply half of mx dot square minus v of x. Is it? Okay, you choose Lagrangian in such a way you recover actually equations of motion. So that means, okay, to this Lagrangian I can add some another quantity such that I still can get the same equation of motion. Okay, Look at the Euler-Lagrange equation. d by dt partial L by partial q dot minus partial L by partial q is equal to 0. So let's say to this Lagrangian I can add a certain quantity, some function. Let's say L plus some constant. Okay. So that means L and L plus that constant, both Lagrangians give you the same equation of motion. The way you are doing the differentiation, let's say x and x plus a will give you the same different result, is it? Under a derivative. Clear? So much sure? Similarly, you can be having, okay, you can think, okay, if I can choose Lagrangian in this way, I can add to this Lagrange another quantity such that that Lagrangian gives you the same equation of motion. Clear? Provided, okay, so you can define some boundary conditions on that term, okay, which you can add. Okay, let me write to this. Okay, let me change this Lagrangian, this very Lagrange, this way. Okay, so there is an arbitrariness in defining the Lagrangian always. So a certain degree of freedom, certain degree of arbitrariness is allowed in this Lagrangian. Okay, you can add certain terms to this Lagrangian such that the new Lagrangian gives you the same equation of motion. Okay, let me show you. Okay, let's change this Lagrangian to some another Lagrangian L plus some df, where df is a total derivative of the function, and I assume this function vanishes at boundaries. Okay, let's say this function okay vanishes is equal to 0 or vanishes at boundary. Clear? So I am assuming this function to vanish at the boundary. Okay, now let's check whether this Lagrangian, now I am having this Lagrangian L prime. Okay, does it yield me the same equation of motion or not? Okay, now let's write. So my S prime will be simply L prime dt. Okay, so what is L prime now? So it's L plus df. Okay, dt. Clear? So you can write same as L dt plus integral df. Okay, so this is a total derivative, is it? When you integrate a total derivative, what it will give me? The function itself. Is that true? Okay, so it will yield me the function itself. So this is what? S plus the function, and it is evaluated at the boundary. The endpoints, let's say A and B. Clear? So it is the boundary term, and this goes to 0. Okay, so this term goes to 0 at the boundary. So what you get? So you get back S prime is equal to S. So that means the equation of motion, what you get from S prime is same as equation of motion what you get from S. Okay, so it means I can define my Lagrangian up to this arbitrariness. Clear? So this kind of arbitrariness, you can think this a coordinate transformation, a general coordinate transformation, such that your Lagrangian changes by a total derivative. Clear? So okay, you got my point? So we call this f to be the gauge function. Okay, you have to customer. So this procedure we call it, okay, or in other words I can say this action is invariant under this kind of transformation. This transformation we call it as a gauge transformation. Gauge transformation you can think as in simple terms as a generalized coordinate transformation. Okay, you got my point? Okay, look why it is so important. From action is a fundamental quantity for any particle, for any field. Okay, so this is a very fundamental quantity from which you can obtain equation of motion. Okay, you got my point? Now if you obtain equation of motion from the action, you require this to be a scalar quantity, this action, so that in one frame of, if you go from one frame to the another frame, so the equation of motion should be the same, is it? So laws of physics should be same if you go from one frame to the another frame of reference. Clear? So that is why you this gauge transformation we call sometimes as a coordinate transformation. So this action must be invariant under such kind of coordinate transformation. Okay, so this kind of transformation, it is actually bigger than the Lorentz transformation. Lorentz transformation is a special kind of coordinate transformation. Here it says some more general coordinate transformation. Clear? So if you are constructing a theory, let's say for some certain field, first you require the action should be, let's say, Lorentz invariant. Okay, the action you are constructing, it should be Lorentz invariant, And additionally you can fix, let's say it should be gauge invariant as well. Clear? Samajh aaya? Okay, you people follow, okay. So in this case, okay, so you can think these are actually, since I am not changing the coordinate, okay, you can think this kind of transformation as an intrinsic transformation at a given point, okay. And let's say you are simply choosing, okay, let's say your field is defined at certain point, let's say at x and t. You don't change the coordinate, but you change simply the field at that very point, okay. Clear? So you know the equipotential surface, okay, you simply choose, okay, you fix the coordinate, okay, you can choose different kinds of potentials at that very point, that will give rise to the same field, is it? Clear? So the consequence of this, okay, I will show later in this lecture, the consequence of this transformation is actually to conserve the charge, okay. So gauge transformation gives you the charge conservation in the electromagnetic field. Clear? We will show that. Okay, so let's write it in the four-dimensional form. Okay, so in four-dimensional form, so our field is defined as A mu. The gauge transformation I will write as A mu prime is equal to A mu minus partial mu this f. Okay, while f is a function which vanishes at the boundary, you can think, okay, clear, as the gauge function. So now you can calculate, okay, so let's take the zeroth component, a0, partial 0, okay. What is a0? That's simply phi, okay. So it's phi prime is equal to phi minus 1 by c, partial by partial f by partial t. Now let's take ai. Ith components will give you the vector a, is it? But it's the lower index. So lower index is having minus. So it will be minus a, it will be plus here. Clear? Sorry. It will be minus again, it is minus. So when you take minus out, it will be plus. Okay. So now let's look at the action. Okay. So the action, what we know for a particle coupled to this EM field, that I denote by SI. So it is E by C, A mu, if you remember, dx mu. Is it? And the free particle case. Free particle does not have the field A. Okay? So it is this very term, okay, which contains A. Okay, so now let's write. So this will go as minus E by C. And what is A mu? How A mu changes? A mu minus partial mu f dx mu. Okay, so that's equal to minus E by C, A mu dx mu, okay, plus E by C, partial mu f, okay, dx. So this is actually the boundary term, okay. So this term vanishes at boundary. Okay, so that's simply as minus E by C. Clear? So it's the same thing. Okay? So this is in the four-dimensional form. Okay? So now let's try to construct what are the invariant quantities we can construct out of the fields E and B. Invariant quantities which are first Lorentz invariant, then gauge invariant. Clear? So that means if you are having an invariant quantity, it means you are constructing a scalar quantity under a given set of transformation. Okay? So what is our field? So what I am constructing, the invariant. So our field is F. So this is a field tensor. Okay, it contains both E and B. I want to construct an invariant quantity. Okay, a quantity which is invariant under Lorentz transformation, and which is a quantity which is quadratic in the fields. Okay, so this is a simple matrix and it contains only linear terms, is it? E's and B's. Okay, now let's construct a quadratic quantity or a quantity which contains fields in the quadratic form. Okay, let's say E square, B square kind of thing, or E into B. That's again the quadratic, is it? Okay, but those quantities are invariant under Lorentz transformation. Okay, and furthermore we can make an additional assumption which are also invariant under gauge transformation. Clear? So, but we will restrict ourselves to what? Lorentz invariance. Okay, Lorentz up to the Lorentz invariance. Okay, so okay, so let's take this F mu nu. Okay, so if I take this kind of object F mu nu and F mu nu. Okay, so let's first construct. So if I make the multiplication, so this this is a matrix multiplication, is it? Is that true? So both indices are contract, so it means it's a scalar quantity. For time being, it's a scalar quantity because it does not contain any free index. Clear? So this contains E and B, this contains E and B, its product will be E square B square or E and B, is it? E multiplied by B. Clear? Then first we see what this quantity gives me. Then we will check whether it is really an invariant quantity or not. Okay, so this is a first non-trivial example of constructing a quantity which contains quadratic fields. Okay, fields in the quadratic form. Okay, clear? Okay, so this week. Okay, so can we? Okay, so this object we write sometimes trace of f square. So you take actually square of this very term, then make the trace. Trace means sum of the diagonal terms. Clear? So because you are actually summing up the terms. Okay? You got it? Okay. So now let's calculate this object. So what it will be? So if I take the diagonal terms, look here. If I take mu, okay, let's take mu as well as mu, okay? So let's take f00, f00. So that's 0 because diagonal terms are 0. Clear? So what are the other terms which are non-zero? So only the off diagonal terms will contribute. Clear? So now let's calculate that off diagonal terms. So one term, let's take mu is equal to 0. Keep this, okay, let's for time being, let's keep mu as such this way, plus then you are having fi nu, fi nu. Is it true? Is it true or not? So I will write now, so f0j, because if I choose now nu is equal to 0, because it's a sum over nu, I have summed over what? Mu I have summed over, okay? Here I goes from 1 to 3, okay? So in this case I is actually 1, 2, 3. Clear? So now if I sum over nu, so nu equal to 0 will be f00, that is 0. So it is f0j plus fij. Fij. Okay? Clear? Now tell me what is f0j? What is it? So f0j is what? Minus e, is it? Okay, so it is minus ej, so it will be simply ej because you are lowering down the special index, is it? Okay, now can you tell me what this fij is? Yes, it is b, is it? But what, how I will write that? Anybody? Oh, wait a second. There is one term which I have ignored here. In this case, I'm sorry. Okay, wait a second. So in this term, actually 0, 0 term is 0. But in this case, if you take nu equal to 0, that's not 0. True? So it will be fi0 plus fij. Okay? And there is a sum over I in this case as well, and there is a sum over I and j as well. Clear? Okay, what is this Fi0? It's now EI. Okay, so what this Fi0 is? Minus EI. Clear? Okay, what is Fij? Anybody remembers? So I told you last time we wrote this Bk is equal to epsilon I, when you say epsilon Kij Fij. Teacher? What is that? Epsilon Ijk Bk. Like this thing. Okay? Fij is like this. So it is epsilon Ijk Bk. Okay, what about this thing? It is epsilon Ijl B. Okay? Because there is a sum over the index k. It's a dumb index. That's why I put a index L. Clear? Okay, so what this is? One instant. Just tell me what this object is. It is simply E dot E. So it is E square. So it is E square minus E square. Okay? Is it true? So it is E square minus E square plus. Then you are having this epsilon Ijk, epsilon Ijl, Bk, Bl. Okay? Now can you tell me what this object is? It is 2s delta Kl. Okay, now you are having two indices are summed up, is it? So if it would have been only one index, then you know the formula, okay? So this again, so if you are having three indices, you know how to put it in the determinant form. So if you are having one index contracted, you know it, you write the product of the delta functions. If you are having two indices contracted, it gives you the single delta function, okay? So now you sum over, let's say k, this k will be replaced by L, okay? So that means this trace of f square, it's equal to minus twice E square plus twice B square. So it is equal to twice B square minus B square. So this object, this f mu nu multiplied by f mu nu, okay? So it gives me what? Twice B square minus A square. Clear? So is it now quadratic in B's and E's? So you are having B square and E square here. Clear? Now let's check whether this is really invariant under Lorentz transformation or not. Okay? Okay. Let's check Lorentz invariance. Okay, so we have this f mu nu under Lorentz transformation. It changes how? Lambda mu, okay, lambda, anybody? Lambda mu delta f lambda delta. Is that true? So this is how it transforms under Lorentz transformation. Clear? Samajh aaya? Samajh aaya? Now look here. So these are two upper indices, okay? Okay, let me give you some idea here. So you are having x prime mu, it goes under Lorentz transformation as lambda mu nu x nu. Clear? So now if I have to write its covariant part like this thing, x prime mu, how I will write? The same lambda. So since these are what? Okay, so it means I need to invert this lambda. Okay, if I have to go from covariant to the contravariant, what I need to do? Okay, let's write it this way. So I can put it this way, G mu nu, okay, x prime nu. Can I write it in this fashion? Okay, so it is G mu nu. What is x prime nu? I know. So you put lambda and put nu here. Let's put some lambda here and x lambda. Clear? Is it clear? But why? Okay, so this is actually from covariant, sorry, contravariant to what? Covariant. Look here, it is contravariant to contravariant. I need to go from where? Covariant to covariant. Clear? So let's write, okay, let me put G mu nu, this lambda nu lambda. Okay, how I can write this thing? G lambda, let's say delta, x delta. Can I write it? So this will raise its index up. Okay? Okay. So this is equal to, okay. Now this, okay. When you apply this G mu on this lambda, where will this nu, okay. So this nu gets contracted. Where this mu will go? It will come at this very point. Clear? So it will be some lambda mu. Okay. Now this lambda will get contracted. It will be replaced by delta. So why it will, this lambda will go to this very position. Okay. X delta. Clear? So I have put actually, look here, I have put this mu here on top left, is it? And then I have put to the, in the bottom, I just shifted, is it? I have not aligned them. Okay, I have not put mu and nu in the same line. Okay, just to remember this thing. So this, if you take mu to be, let's say, row index, you can take the nu as the column index. Clear? So much here? Okay, so now what is the difference here? So it is simply, so the difference between this lambda mu nu and this lambda mu nu is what? Rows and columns are interchanged. Clear? So it means this has to be actually inverse to this thing. समझ आवा? तो mean का समझ? Everybody followed it? What I am saying? Okay, now let's check whether it is really true or not. Whether it happens this way, whether this is inverse to this object or not. Okay, so let me do that first. Then. Okay. So let's calculate the length. Okay. Okay. So let's write this length. Okay. So this is the length. X mu x mu. Does this represent the length of the vector?
Yes, sir.
So it is simply x square. So let's write how the length changed. Okay, so the length under Lorentz transform, it should remain fixed, is it? So it's an invariant quantity. So now let's apply this x prime mu. What is x prime mu under Lorentz transformation? So it's lambda mu. Let's write some, okay, lambda. So then you put x lambda. Okay, for this x, what is x prime mu? So tell me, what is x prime mu? You put lambda mu. Okay, let's write some delta. X delta. Clear? Okay, so that means lambda mu, lambda. Okay, lambda mu delta. So x lambda, x delta. Clear? You people followed it? Okay, so this must be equal to what? Tell me. What this must be equal to? Simply x mu, x mu. Clear? So then I can say it like this thing, x prime mu, x mu, okay, x prime mu. So that should be same as what? X mu, x mu. Okay, so the length is invariant under Lorentz transformation. Okay, so now that means I need to put this x lambda, or I need to put it in x lambda and x lambda form. Clear? Okay, so let me write it lambda mu lambda, lambda mu delta. Okay, so I will write this x lambda. Okay, so this x lambda, can you tell me how I can write it? Okay, so let's write some g. Anybody? Let's write some g delta. Let's put some index nu x nu. Clear? Is it okay? Okay, so it is g delta nu lambda mu lambda, lambda mu delta, x lambda x mu. So this has to be equal to what? This has to be equal to x mu, x mu. So that means I can write like this, and it should be equal to x lambda, x lambda. Can I write? So that's equal to x lambda. I will write g lambda nu. Okay, x nu. So g lambda nu x lambda x nu. So this has to be equal to this object. Clear? Now it means, so you are having these two things same. You can compare now the coefficients. Clear? So this is only true when this coefficient is equal to this thing. So then you can say, okay, this x prime is same as xx. Clear? So it gives me g delta nu okay. So now you can raise, okay, what you can do, okay, so this is the way, okay, now what this is, so is this an, like say matrix A multiplied by its inverse is equal to identity? So what are the elements of this G lambda? It is diagonal, okay, 1 minus 1 minus 1 minus 1, is it? Clear? But if I raise, let's say if I raise this index nu up, let's take this nu here, so it is G nu lambda, is it? Like this objective. So it will become G nu lambda. Okay, let's calculate this G00. G00 is 1. What about this G01? Let's say it's 1 again, is it? Because I have, okay, if you know G mu nu, you know it contains 1 minus 1 minus 1 minus 1, clear? But if you take G01 in this way, that means you are lowering down a special index, clear? So it gives you the plus 1. So that means if I write the G nu lambda in this fashion, so it is simply what? Delta nu lambda. So it's simply an identity matrix, clear? So it means, so if this, okay, when you raise this nu here, okay, you take this nu here, you take this nu here, so it's simply an identity matrix and this identity matrix, clear? So in other words, you are having lambda multiplied by some lambda is equal to an identity. What it means? When you are in A, B is equal to identity, it means B has to be inverse of A or A has to be inverse of B. It means this object must be what? It should be inverse of this thing, or this has to be inverse of. That's why I have put it in this fashion. So lambda mu nu this way and lambda mu nu delta. But I will, okay, when I will be writing, it means I will be writing them in the aligned fashion. Clear? Okay, so you need to, from the perspective, you should understand what I mean. So, samajh aawa? Everybody followed it, what I am saying? Huh? Shall I repeat or not? Okay. Clear? So, so what I am saying is, okay, let's write this G nu lambda. Okay. Okay, let's look at this. If you can raise this up, let's take this nu here, clear? And take, you need to take nu up as well, clear? Because nu is a free index, lambda is a free index, clear? I think here's some gadbad has happened. Something has happened in this equation. The free index should come from here. Somehow there is a, okay, well, let's say this is the crux of the equation, what I am saying. Okay, so let's raise this index up. Let's write G nu delta and it will be G nu lambda. Okay, let's take that G nu mu. Okay, let's write this. Okay, so you are having the G mu nu. So it's like this thing, 1 minus 1 minus 1 minus 1. Clear? Let's write the G mu nu in this fashion. Let's write this way. Okay, what it gives me? Let's take G00. Let's take first G00. What G00 gives me? It comes from actually G00. What is that? 1. Okay. Now let's take G01. Sorry, G11. Let's take G11. Clear? Let's take a diagonal term. G01, those will be all 0. I need only diagonal terms. Let's take G1. What I have done? I have actually lowered down one special index. When I am lowering the special index, what will happen? Minus 1. So you will be having minus 1. Then you multiply what is G11. So what is that? Minus 1. So that is plus 1. What will be G22? That's again plus 1. What is G33? Plus 1. So that means all the terms will be identity. Clear? So that means this G mu nu is same as what? This delta mu nu in 4 dimensions. Clear? समझ आवा? समझ आवा? So in other words, I can write it in this way. So this identity I put in this fashion. So there was an index error, you need to figure it out. Somewhere is an index, actually the identity is in this fashion. Okay. So this is the identity. G mu nu, you put some lambda mu, you put them lambda nu, okay? Put some lambda delta, okay? Like this thing, so that's equal to G delta delta. So this is actually the identity, or simply, or you can write it like this thing. Lambda, okay, let me write in the aligned fashion. Lambda, let's write some lambda mu, so that's simply delta mu. So one index is contracted, another remains. So I will be using this identity in a moment. That's why I am showing it here. Clear? So this is simply समझ आओ? So I am aligning them now. So it means this is inverse of this thing. Now you know what exactly inverse means. समझ आओ? Okay, you will be understanding it in a moment when I apply this result. What exactly I mean by that. Okay, so let's take this f prime. Okay, so you are having this f prime mu nu. It goes as lambda mu. Okay, lambda nu. Then let's say f alpha beta. That's right, alpha. Clear? So therefore I can write this f prime mu nu and f prime mu nu. So this object. So I am doing the Lorentz transformation. Okay, so for this I have written already lambda mu alpha, lambda mu beta. Okay, f alpha beta. Clear? So now for this f mu nu, I will write lambda. So this index first mu, then another lambda with this index mu. Let's write some. Okay, some lambda and sigma. F lambda sigma. Clear? True? Okay, so let's plug the terms. So it is f mu alpha, sorry, lambda mu alpha, lambda mu beta, then lambda, lambda mu, okay, lambda sigma nu, then you are having f alpha beta, f lambda sigma. Clear? Now let's look which terms where the indices are contracted. So now look at this term and this term. What they have? Mu is contracted, is it? Is mu contracted? So you are having lambda mu alpha, lambda like, okay, let me write it in this way. Then you are having lambda nu beta, okay, lambda sigma nu, okay, f alpha beta, f lambda sigma. Clear? Now what is this? So one index is contracted, so it gives me, okay, it is in this fashion. Lambda mu lambda, okay, lambda lambda nu, okay. So lambda is contracted, what it gives me? Delta mu nu. Okay, so you are having mu contracted, what it will give me? Delta of lambda alpha, okay. So it gives me simply delta lambda alpha. So it will give me delta sigma, sigma beta, f alpha beta, f lambda sigma. Clear? So now let's sum over alpha. So when you sum over, let's say lambda, so this lambda will be replaced by alpha. Okay, when you sum over, so this is sigma. When you sum over sigma, sigma will be replaced by beta. So it's f alpha beta, f alpha beta. Is this the same thing? Is this the same thing? So that is the same thing, f mu nu, f mu nu, because these are domain indices. Alpha and beta are domain indices. So it means this quantity f mu nu, it's a invariant quantity. It's invariant under Lorentz transformation. Clear? So that means we have constructed. So it's a true scalar. True scalar in a sense. If I, let's say, change from one coordinate system to the another. Let's say if I make a reflection about origin. If you are having a true scalar, it will remain as a scalar. Let's say you are having a scalar quantity, you reflect about the origin. Its reflection will be the same thing. Clear? But if you are having a pseudo scalar, it will simply change a sign. If you reflect it by the through the origin, okay, let's say you are having a coordinate system, you are having a scalar quantity here. When you look it from the another point of view, true scalar will be the same thing. But under the coordinate transformation, it will change a sign. It will remain a scalar, but with a sign change. Those scalars we call as a pseudo scalars. Clear? So this is a true scalar. Clear? It does not change the sign. Okay. Now let's check whether this is gauge invariant or not. Okay? Let's check. So you are having this f mu nu, f mu nu. Okay? So what is F mu nu? It's partial mu A nu minus partial mu A mu multiplied by partial. Okay? So it will go as, so now let's make a gauge transformation. So you are having a gauge transformation. So you, this partial mu, okay, now what will be A nu? Just right? Just tell me what will be A nu? So A nu will be simply A nu minus partial nu F, okay? Then minus partial nu, what is this A mu? It will be simply A mu minus partial mu F, clear? So then you are having this objective partial mu, A nu is A nu minus partial mu F minus partial mu A mu minus partial mu F. Okay? So that's equal to, okay, let's multiply. So it's partial mu A mu minus, okay, tell me, partial mu F, okay, yeah, on this thing, minus partial mu A mu, okay, minus and minus is plus, partial mu F. Like this thing, then you are having partial mu A nu minus partial mu F, okay, minus partial mu A mu, minus and minus plus, partial mu F. Okay, so this term cancels with this term, so this term cancels with this term. What remains here? Partial mu A nu minus partial mu A mu. It is same as F mu nu, and that's again as F mu. So it means this quantity is what? Invariant under gauge transformation. Okay, so it means this is invariant under gauge transformation. Okay, so that means we have two properties of this thing. So it's a, so this kind of scalar. Another scalar which is not important to us, but I will mention it. Okay, so second scalar is like this thing: epsilon, alpha, beta, gamma, delta, F. So this is another scalar: alpha, beta, gamma, delta. Alpha, beta, gamma, delta, they are contracted. So this is another scalar. You put a half here. So let me know. So this is another scalar which we can. Okay. So this is again what? The product of two f's. So it means you will be getting what? Quadratic things. Clear? Now, but there is an epsilon this way. If you remember. So if you remember this epsilon ijk when we were doing vector analysis, it was some er dot ej cross ek. You remember it? Clear? So if I change my coordinate system, let's say if you reflect through the origin of the coordinate system, clear? So what will happen to this thing? So it's a parallelepiped, is it? So it will, you will look it in the other way around. So these vectors will change the direction, clear? So how many vectors are there? 3 vectors. So how many you will get? You will get a negative sign. Clear? So when you change, okay, when you reflect, let's say you are having a parallelepiped, okay, divided of these unit vectors, ei, ej, ek, and you reflect it through the origin of the coordinate system, it is simply what we call it the parity transformation. Clear? So that means you take x to minus x. Samusha, it means the reflection about the origin. So what will happen? So this epsilon ijk, this will simply change the sign. Clear? So it means this epsilon ijk, if it's multiplied with certain quantity, it will give me the pseudo-scalar nature. It will remain a scalar, but it will be what? It is not a true scalar. Clear? So that is, so this actually the 4-dimensional form counterpart of this 3-dimensional. Okay? So this epsilon ijk, you are having now 4 indices here. Clear? It is the same objective. I have already introduced this objective. You remember it? Huh? Okay. So that means with the help of this epsilon, alpha, beta, gamma, delta, this very object, the scalar quantity which I will be obtaining from here will be what? A pseudo scalar. Clear? So, okay. So you know this epsilon alpha. I have introduced it. Huh? Have I introduced it somewhere? Okay. So it is the same thing. You are having epsilon I, j, k, l. Okay. So it is plus 1. If all indices are taken in cyclic order, minus 1 anti-cyclic order, okay, and 0 if any pair of indices is same. Clear? Okay. So let's look at this very thing. You can check yourself. It is a Lorentz invariant quantity. Now let's calculate what exactly this object is. Okay, let's calculate it. Okay, now tell me. Okay, this is very tricky to calculate. Rather, it's very simple. Now I have told you if any pair of the indices alpha, beta, gamma, delta is same, then it is 0. Okay, so that means all must be distinct. Let's say alpha. Okay, alpha. All these indices take value from 0 to 3. Clear? Let's say if I fix alpha equal to 0, then what they should be? No, they should be actually, these indices should not be equal to 0. First thing is that. They can be, okay, this beta can be now 1, 2, 3, this gamma can be 1, 2, 3, this delta can be 1, 2, 3. Now if I fix beta to be 0, then other indices cannot be equal to 0. So let's do it. So I will write it now this way. Alpha, okay, so let's write. Let me write alpha. If I write this alpha equal to 0, then beta I can put I, j, k. While I, j, k take values from 1 to 3. Clear? Okay, so I can write this f 0 I f j k. Can I write it? Then next term I can write epsilon. Let's write the other term. So let me write, okay, beta to be 0, others will be like this thing. Can I write it? F I 0 f j k. Can I write it? Okay. Now I can take now another I j 0 k f I j f 0 k plus epsilon I j k, another is 0 f I j f 0. Clear? Now if you see, are they all these terms same? So let's say if all, okay, let's take this very term. Okay, take a look at this very term. I can interchange what? Let's say if I interchange I and 0. Okay, look here, everybody. Let's interchange I and 0. On interchanging I and 0, it will yield me a minus sign, is it? It's an antisymmetric tensor. So I will interchange I and 0 here as well. So this will also give me what? A minus sign. So here if I interchange, okay, I and 0 if I interchange, so it gives me minus sign. Here it gives me what? A minus sign again. I 0 interchange. So I will get what? 0 I j k 0 I, is it? The same term here. So minus sign minus plus. Correct? So similarly if I interchange no what? Okay, so you can interchange 0 j then 0 I. So it will be same thing. So you are having the same thing f0 I. So because k is a domain index, so it doesn't matter. You are having the same form here. The similarly here. Okay? So all these terms are same. So it means I am having 4 times epsilon 0 I j k f0 I f j k. Clear? Samajh aaya? Okay. So I can write 4 epsilon 0 I j k. So I am having f0 I. Okay, what is f0 I? It is ei. Clear? Now what is fjk? Is it minus ei or plus ei? It's I think minus ei. Yeah? What is fjk? We have written it. Epsilon jk l d. Clear? Clear? Now this epsilon 0 I j k acts in the same way. So now one index is 0. This will act in the same way as epsilon I j k. Clear? So forget about the 0. So it will act in the same way as what? I j k. Clear? So this is saying minus 4 epsilon I j k. Okay, then you are having epsilon j k l e I d l. So can you tell me what this object is? So we have written is twice delta. Okay, j k are there, so I l e I d. Okay, so you sum over I, so you'll be getting minus 8 e I d I. So that is minus 8 e dot vector d. Clear? समझ आया? So we are having another quantity. We write it. So another scalar quantity, what we constructed from this fs. So it is half of. Let me write half of epsilon alpha beta gamma delta. So that's what when I divide it by half, so it will be simply minus 4 e dot. The home assignment will be just check it is Lorentz invariant. Clear? So you need to okay. So under Lorentz transformation, every index will have that lambda. Okay? Clear? So you do it in the same way. समझ आओ? So these are the two invariant quantities. Okay, which are invariant at Lorentz transformation, and they are actually the scalar quantities. Clear? So how much time is remaining?